How's it going? So we have spent in chapter one a few days on linear equations. We've spent a few days on quadratic equations. So now we're going to kind of throw out there some other types, radicals, rationals, and some polynomial equations today. I'm going to start with a rational here. And this actually, we did this in 1.1. It was a rational type of equation like this, but you'll see that as we get to the end, it's going to be a little bit different than what we did in 1.1. So to start with, I am going to, typically what we do is try to get a common denominator. So you want to factor all those denominators first, and I can see that this would have a GCF that comes out. And how lucky are we that it factors to the exact same two factors that are sitting over here. So that's handy, and they tend to be kind of nice about doing that. So if I were to look at what is my common denominator, I've got to have a lone x like this, and I've got to have a quantity x minus 2. That's going to be my common denominator. Now, before I jump in and start solving, remember, anytime we dealt with these rationals, we always wanted to have an awareness of what our domain was. And now that we're solving, that's really important. So looking at the factored version, I would want to make sure that x does not equal 2 or 0. Those would be the two things that would make a denominator 0 in this equation. So at the end, I want to check and make sure I didn't really get either of those. Now I'm going to go ahead and start getting this common denominator. This first equation or first term is missing an lone x, so I'm going to take it times an x. The second term is missing an x minus 2, so I take it times x minus 2. And the next one has everything it needs, so I don't have to change it. Now I usually set this up with one big fraction with the common denominator. It's going to equal another fraction with the common denominator. Now on the right side here, we're not doing anything. That's just going to stay a negative 2. But on the left side, we've got some work to do. This x is going to get distributed through the 3x plus 2. So now I'm at 3x squared plus 2x. And then my plus 1 is going to distribute through the x minus 2. Be really careful. Remember, when this is a minus sign, I'm still getting people that are forgetting to distribute that minus through the parentheses. Now this is a plus, I don't have to worry about it. In fact, it's a 1, that makes it even easier. I just have a plus x minus 2. The point of getting the common denominator all the way through is that we are allowed to then multiply both sides by that denominator, and boom, it goes away. And all I have left then is a 3x squared. I'm going to go ahead and combine like terms there. And the fractions are gone. That's our goal, with getting those common denominators to make the fraction go away. Now I can see here that I've got a quadratic. That's what's new today from 1.1. In 1.1, when we got to this stage, this was always a linear equation. Now you're going to start seeing a quadratic here. So we have all these ways of solving a quadratic. It's going to look like one I'm going to try to factor. In fact, look how nice this is going to play out. When I add 2, that's going to go away. That's going to make factoring really easy, because then I just have a GCF. I'm going to pull out a 3x, and I'm left with x plus 1. So then my solution is going to be 0 and negative 1. However, remember up here, the domain, x can't be 0. So even though I got it here, I have to put a big X through it to show that it doesn't check back in the problem. I love to see that you found it and then you just put a big X on it saying that you checked it and it didn't work. Now, because we really did this already in 1.1, I'm not going to spend time to do another equation. They kind of all play out the same way. Always want to be checking. Sometimes you'll get both of these answers to work. Sometimes one does not. Sometimes both of them don't, and you end up with no solution. So anything's fair game. Just process is the same always. Let's move on to a different type of problem. I know we all love the application type of problems, so let's work on some of those. This is a little bit different than our previous ones. These are work rate problems. And so I feel like I've tried to make this very straightforward on how to set these up. So take some nice notes here. So the amount of work that you complete, and we use a capital A to indicate the amount of work completed, is found by multiplying the rate at which you work. We're going to use an R for rate, and the amount of time that you work. It's sort of like distance equals rate times time. Here, the amount of work you get done is your rate times the time that you spend doing it. And you might box that in. That's going to be a formula you're going to need to remember. Now, the rate is how much of the job you can complete in 1 unit of time. So how much can you get done in 1 day or 1 hour or 1 week? What is it? So usually how it's indicated, though, is that you find out, it takes 3 days to complete a job. Okay, if it takes 3 days to do the job, you have to break it down to what can you get done in 1 day. So then your rate would be 1/3, because you could get 1/3 of that job done. So ultimately, whatever this value is becomes your denominator, and that's what your rate would be. So if it took you 5 days, you'd have a rate of 1/5. Took you 10 days, you'd have a rate of 1/10. Now, what we're working on is having 2 people or 2 things working together to complete a job. So you'll take the amount of work the first person does, add it to the amount of work the second person does, and it's always going to equal 1 completed job. Let's look at an example here. Lisa and Keith are raking the leaves in their backyard. Working alone, Lisa can rake the leaves in 5 hours, and alone Keith can rake them in 4 hours. How long would it take them to rake the leaves working together? All right, the first thing I want you to do is go ahead and come up in your mind, what do you think the answer is? I don't know. What's a reasonable answer? What do you think? Go ahead and jot it in the margin. I'm going to give you a couple seconds. You got to commit. You got to write something over in the margin. Okay, so I'm going to guess that some people say that it takes 9 hours because there's a 5. If Lisa can do it in 5, Keith can do it in 4. Together, they're going to do it in 9. Okay, I hope you didn't say that because I get it. It seems like maybe that's what you do, but it doesn't make common sense because Keith can do the job all by himself in 4 hours. If Lisa's going to help him and it's going to take him 9 hours, I'm thinking Keith doesn't want Lisa's help, right? I mean, it can't take longer than 4 hours. Otherwise, Lisa isn't really helping. So your answer, whatever you estimated, better be less than 4 hours because Lisa's supposed to be hurrying Keith up a little bit here. All right, so, I don't know. Less than 4 is what I was hoping you were saying. Now, how long would it take them to rake the leaves together? We've got a formula for that. It's this right here. So I'm going to set this up, and I'm going to write it like this. The amount of work that Keith does plus the amount of work that Lisa does. Those are just subletters to indicate which A we're dealing with. And together, it should equal 1 completed job. Now what I'm going to do to figure out the amount of work that Keith did, I'm going back up here to this formula. I'm going to take Keith's rate times his time. Since Keith can rake by himself in 4 hours, then his rate is 1/4. Times, how long is he going to work? Well, we don't really know that. Isn't that the question? How long will it take them? All right, so his time is T. Plus, now let's do it with Lisa. Lisa can do it by herself in 5 hours, so that makes her rate 1/5. Now she is working right alongside Keith the whole time until the job's done. So she's working the same amount of time that Keith did. Equals 1. Now the next thing I would do is I would go ahead and I would take these T's and look at them like they're a T over 1 and pop them up to the top. So this 1/4 of T is really the same as T over 4 plus T over 5 equals 1. Now we're going to get a common denominator of 20. So take this one times 5, this one times 4. I think of this as a 1 over 1, and this is going to be a 20 times a 20. So I am left with 5t plus 4t over 20 equals 20 over 20. Multiply both sides by 20, and I have 9t equals 20, divide by 9. And t ends up being 2.2 repeating. All right, now I think on your homework, they're going to want you to leave it as the 29ths, but 29ths is hard to understand what that is representing. So it is kind of nice to change it to a decimal, but I don't love the decimal either. So what sometimes they'll have you do, I don't think they have you do any decimals on your homework. They're going to want it exact. So unless your decimal comes out exact, we're going to write it like this. 2, and it goes in there twice with 2 left over, so 2 and 2/9. That's how long, oops, sorry, forgot to label. Don't forget to label. For sure, don't forget to label. 2 and 2/9 hours. That's how long it's going to take them to work together to get that job done. Let's try it one more, but let's tweak it a little bit. All right, in this example, instead of giving us exact numbers, it says one printer can do a job twice as fast as another. Working together, the printers can do the job in 2 hours. How long would it take each printer working alone to do the job? So it's sort of backwards. This time, I know how long it takes them to work together. What I want to know is how long it takes them individually. So it's backwards from Keith and Lisa. Now, remember, if it takes 3 hours to complete the job, then the rate is 1/3. If you don't know how long it takes, then we're going to say it takes X hours or T hours, which means the rate is 1 over X or over T, however you want to do it. Now that's going to be your faster printer because the faster printer took X hours. So the slower printer would take twice as much of time. So the slower printer would take 2X, which means its rate is 1 over 2X. So those are the rates of our two printers. Now, they also told us that they're going to work together for 2 hours. So I know what my time is. So I'm back to the amount of work the first printer does is its rate times its time, which we know is 2 hours. And the second printer, the slower printer, is going to be 1 over 2X. It's also going to work for 2 hours. And together it equals 1 complete job. Just like last time, you take this number out here and think of it as 2 over 1 and pop it to the top. So this one's going to be 2 over X plus the next one is going to be 2 over 2X. But wouldn't these 2's reduce? There's no reason not to reduce those. Let's go ahead and reduce it. And now I'm down to 1 over X, and I'm already going to have my common denominator. Equals, I guess I'm going to go ahead and think of this and get my common denominator right here, save myself a step. It's going to be X over X. So now when I take both sides of the equation times X, all the X's cancel, and I have a 2 plus 1 equals X, so X is 3. Now let's remember, what did X represent? Did we even find what we need? What would I label this? Well, X is how long it takes in hours for that faster printer. So it's going to take the fast printer 3 hours. The slow printer takes twice as much time, so it's 2X. So my final answer here would be that the fast printer is going to take 3 hours by itself, and the slow printer would have taken 6 hours by itself. All right, so I could go on and on, but I feel like that kind of represents the examples pretty well from your homework. One thing that might happen, in fact, it does happen, what if they weren't working together? What if one was trying to do something and the other one was undoing it? Like, so if you work together to complete a job, then you're going to add the two work efforts together. But if you have one item doing a job and the other item is undoing the job, then you'd have to subtract there. You'll know what I mean when you get to those problems in your homework. Let's try some radical problems. Now, this is a typo here. I think I fixed it in your notes. This right here should not say variable. It should say radical. Now, two situations that I have here. One of them has a single radical in it. This is going to be the easier scenario. When we have two radicals, now that gets to be a little bit more challenging. Let's start with the easier one. Maybe start way over on the left and leave yourself some room to work through the second problem. Over here, first thing you're going to do is isolate the radical and then raise both sides to the power of the index. All right, isolate the radical. So I'm going to subtract the 2. And then I'm going to square both sides to get rid of that radical. Now, you don't just get to square each thing individually. You are squaring each side as a group. So on the left, the squaring and square rooting undo each other. On the right, you have to square the binomial. I'm telling you, if you have not learned that shortcut yet, it is time to do so. We do so much of this. You need to be able to do this without having to write it out and do FOIL every time. So square the first term, multiply the 2, and double it. Square the last term. Okay, I can see what I have left here is a quadratic. So it looks like maybe a factoring problem. I'm going to bring everything over to the right. So I'm going to have an x squared. When I subtract the 2x, I get negative 6x. Add the 1. I get a 5. And it's going to equal 0. Yep, this is going to factor beautifully. Factors are going to have to be 1 and 5, x and x, signs are the same, both minuses, and yep, that gets me a negative 6x. So I get as a solution 1 and 5. But here's the deal. When you go through the process of solving and you square both sides, you're suddenly creating this quadratic that has 2 solutions. But it didn't start off that way. So what happens is we introduce in this solving process, sometimes we introduce extraneous solutions, extra solutions that don't really work in the problem. And I promise it happens quite a bit in this scenario. So you do have to check your answers. Make a note to yourself. You got to check these answers. And not that it makes it like undefined, like in a fraction or something with your domain, but just does it even work in the problem? So what you're doing is you're taking 1 and you're going to plug it in for this x and for this x. All right, so if I plug in a 1 here, all right, so I want to do all of this work and have it equal 1. Let's try it. If I put a 1 here, so that's a 2 minus 1, that's 1. Square root of 1 is 1, and 1 plus 2 is 3. That is not 1. That does not work. Big X. 1 does not work. Let's try 5. Okay, so I'm going to put 5 here. That's it. Okay, so again, I want it to equal 5 because I'm going to put a 5 here and I'm putting a 5 here. So whatever I do here, I want it to equal 5. So that's going to be 10 minus 1. So that's 9. Square root of 3 or square root of 9 is 3. And 3 plus 2 is 5. Boom, it checks. All right, I like it. 5 is my answer. Had to cross off the 1. Let's look at our next example. It's got 2 radicals in it. So if you have multiple radicals, you want to get 1 on each side, and then you're going to raise it to the power of the index. All right, so same as before. This can be easy, but the one I gave you, not super easy, because when I move the radical to the other side, I'm going to write really little on this example. I add that over, and now I have a 1 plus square root of x plus 4. That 1 is really going to mess me up, because when I try to square both sides, I've got to square it as a group. works great on the left, but on the right, I actually have a binomial that I'm squaring. You cannot just distribute a power. I've got to think of it like it's written out twice and I'm foiling it, except I'm doing my shortcut. Take the first term and square it. Multiply the two, which is just a square root of x plus 4, and double it. So it's a 2 square root of x plus 4. If you square the last term, it's just going to undo the square root and you get plus x plus 4. Well, our goal was to be rid of radicals, and you can see we didn't quite make it. But what happens is you get it down to 1 radical. So it starts off with 2. You got to square both sides. You're still going to have a radical left. You're going to start all over. Let's isolate this radical and then square both sides. So I'm going to peel stuff over to the other side. If I subtract this 1, those are going to cancel out. That's nice. I'm going to subtract this x. That's going to get me a 2x. Subtract the 4. And I have 2 square root of x plus 4. Now I'm going to go ahead and I'm going to divide both sides by 2 because it's going to divide so beautifully. Some people like to just at that stage right there square both sides, and that's okay. If this didn't divide so nicely, that wouldn't be a terrible idea. But if I were to square this, I'd have to square this and get a 4, square the square root and get x plus 4, and then that 4 would have to distribute. That's how that would look. You might choose to do that on your homework. But here, it just divides beautifully, so I'm going to take advantage of that. Divide each term by 2. And now I'm ready to square both sides. All right, we get an x plus 4. Over here, I'm going to square the binomial. That's an x squared. Multiply the 2 and double it. Add the 4. All right, got myself a quadratic, so I'm going to bring everything to the left so that equals 0. Ooh, lucky there. 4's cancel out. Going to make factoring much nicer because I can just pull out the GCF. So it looks like I'm getting x to equal 0 and 5. Now let's do a test. I'll do 0 if you do 5. I put in a 0, I'm going to get the square root of 1, which is 1. Put in a 0, I'm going to get a square root of 4, which is a 2. And 1 minus 2 is negative 1, not 1. 0 does not work. Did you test 5? If I put in a 5, that's 15 plus 1, so there's a 16. Square root of 16 is 4. Put in 5 here, I end up with the square root of 9, that's a 3. And 4 minus 3 is equal to 1. So the 5 works good. I've got a solution. Okay, so there's a couple examples with radicals. Let's move on. What if it's not a square root? What if it's a cube root? Well, no big deal. I'm just going to, in this case, get a radical on either side. I was nicer here because you just have a 0 on both sides. So you're going to have a cube root of 4x squared minus 4x plus 1 equals, and I'm just going to add this over. The 0 doesn't do anything. And now I just get to cube both sides. Cube and cube root undo each other. I get 4x squared minus 4x plus 1 equals x. It's a quadratic. Let's set it equal to 0 and see if we can't come up with some factors that work. I'm going to come up here. Well, I know the 1's got to be a 1 and 1. Oh, and my signs are the same, both minuses. Kind of feeling like I should go with the 4 and the 1. 4x and x gets you a negative 4x and a negative 1x. That's what I want right there. So x is equal to 1/4 and 1. So I'm going to test the 1 here with you. So that's going to be a 4 minus a 4, that goes away, plus 1. All right, the cube root of 1 is 1. And when I put 1 in here, I'm going to have a cube root of 1. That's 1. So 1 minus 1 is 0. All right, 1 checks. For the 1/4, if you're good with your mental math, you could do that, just plug that in and just track it through, or you can put 1/4 in and run it through on your calculator. I'm going to let you run it through on your calculator. You decide if it works or not, and then cross it off if it doesn't. I'll wait while you do that. All right, I don't have time to wait. I'm going to just tell you it works. Okay, I plugged it in. Let's keep going. Let's try this next one. I'm going to move on to polynomials. This problem looks like a factoring problem, except that, oh, wait a second, it's an x to the 4th with an x squared. All right, because this is a 4th and this is a squared, this actually is a factoring problem. It's just that instead of x and x, I'm going to put x squared and x squared. This only works because this is a 4th degree and this is a 2nd degree. Because when I do my outer and inner, I'm going to end up with an x squared term. Factors the 9, I'm going with 9 and 1, a negative 9 and a positive 1. Now this is equal to 0, so I'm actually going to go ahead and set each equal to 0. X squared plus 1 equals 0, so that means x squared would equal negative 1. This one, I'm going to add 9 over, so x squared is going to equal 9. This plays out nice. Now remember that because this is a 4, I should be getting 4 answers here. Don't forget, square root, you've got to put your plus or minus on there. There's 2 of my answers. When I square root over here, I have a problem. The square root of a negative is going to be imaginary. That's all right. X is equal to plus or minus I. And those are my other 2 solutions. So anticipate some weird stuff happening. You might get a fraction here. Definitely could end up imaginary. If it does happen to be a fraction, make sure that you have your denominator rationalized. And don't forget that plus or minus. I do think your keyboard on MyMathLab has a plus or minus option for you. All right, last thing. What if you have rational exponents? That means these ugly little exponents that are fractions. Well, they might look scary, but they're really quite easy to get rid of. You're just going to raise both sides to the reciprocal power. If you end up with even roots, that would be like if you were end up doing a square root, then you got to do the plus or minus. Don't forget that. But if you end up doing odd roots, we don't do plus or minus. So let's look at this first one. I want to isolate the variable. Let's add the 6. And let's divide by the 3. And right now, I am ready to raise this to the reciprocal power. So this is going to be to the 4/3. So that's going to play out nice. That means I'm going to take this one to the 4/3 power. So x is equal to. Now, sometimes you're going to get problems that you can actually reduce and do something with. This one, not so much. Notice that this right here is a cube root. I'm going to take it to the 4th power and I'm going to cube root it. The cube root means I'm doing an odd root and I don't do the plus or minus. It's going to look like this. The cube root of 2 to the, actually, I'm just going to go ahead and write of 16. That's 2 to the 4th. This does break down because 8 is the perfect cube that goes in there. So it's going to turn into 2 cube root of 2 when you reduce. And I don't know why I put a cube there. That cube is gone. All right, let's try one more. This time, instead of having a single variable to a power, you have this quantity to a power. So it's already isolated as best it can be. So I'm just going to go ahead and take it to the 3/2 power, other side to the 3/2 power. These cancel out each other. I just get x plus 5 equals, and this is one of those ones that, well, a couple things. Notice that you're going to end up square rooting, and then you're going to cube it. Well, 4 actually does square root, so this is going to come out great. But also, since I'm square rooting, I have to do my plus or minus. So let's do it. It's going to be a plus or minus. The square root of 4 is 2, and 2 cubed is 8. Subtract your 5. X would be, let's see, if 8 was positive, you'd get a 3. If 8 was negative, you'd get a negative 13. And those are your solutions. Okay, nice sampling of different, weird, different kinds of equations that you come across in math sometimes. Go give it a shot. Good luck.